Possibly the most important topic that I'd like to start with is the selection of metal within your probe. We carry 4 different classes of metals: tungsten, platinum, iridium alloy, iridium, and alloy or stainless steel, which are actually 2 different metals, but they perform very comparable to each other, so I'm lumping them together as one. I'd like to start with tungsten. Tungsten is a very versatile option. It's widely used microelectrode material, offers a great balance between performance and cost. Some of the advantages of it, for why you should select it, are that it's extremely strong and stiff with great rigidity. It keeps its straightness very well when implanted deeply into tissue. It's great for acute and short-term chronic recording with a long published history of use. Tungsten has been being used in probes for a very long time. There's many papers that discuss its performance very well. It's also fairly biocompatible and non-toxic with great corrosion resistance, and it also has a very affordable cost. Some of the disadvantages of it are that it's not ideal for stimulation. Tungsten has a low charge transfer capacity and a high concomitant impedance, as well as reduced electrochemical stability compared to the other metals. This means that for the same surface area, tungsten tends to have a higher impedance, which means that it more quickly approaches unsafe potentials, with the application of the same stimulus current. It also gives less consistent long-term recording because of this reduced electrochemical stability. I personally have seen tungsten dissolve in the body after long periods of time, particularly when in acidic conditions, such as you'd see from aggressive tissue response or inflammation. Second metal option is platinum iridium alloy. Platinum iridium is becoming the gold standard for many for chronic recording and microstimulation, mainly because it has great electrochemical characteristics compared to tungsten, particularly its electrochemical stability. Platinum iridium is much more noble, has a high charge transfer capacity, low concomitant impedance, which means that it's excellent for stimulation. It's also very versatile. It gives consistent performance in pretty much all applications. However, some of the disadvantages of it is, of course, that it has a greater cost than tungsten, as well as alloy and stainless steel, which make it less appropriate for acute and non-intensive chronic recording, where tungsten gives more or less equivalent performance. For acute and non-intensive chronic recording, there's really not a big advantage to using platinum iridium, which is why we steer people towards tungsten in those applications. However, for those that are doing critical long-term chronic implants as well as stimulation, platinum iridium is always the way to go. However, platinum iridium is also vulnerable to corrosion in some high-intensity stimulation situations, which is why for those that are doing these types of studies, we recommend moving to pure iridium. Pure iridium is the most intensive stimulation conditions and protocols. They offer unparalleled performance. They have excellent hardness and rigidity. It's one of the hardest metals known. Has great corrosion resistance. Also has pretty much greatly superior charge transfer capacity and concomitant impedance compared to the other metal options. It can handle very small surface area. It can also be activated, which gives it even better performance. Or activation, current is run through it, which causes the growth of an oxide film, iridium oxide, which has many fast Faradaic options available to it, offers a lot of density. Some disadvantages are, of course, is that it has a very high cost compared to other metals due to its specialty nature, and it is only available in 100 micron diameter. Last metal options are alloy or stainless steel. As I mentioned earlier, these are actually 2 different metals. Alloy is cobalt chrome based, while stainless steel is, of course, iron based. However, they both have comparable performance and cost, and they're best for budget and specialty applications. Very versatile metals. They offer great acute and chronic recording performance, and they have a low cost compared to the other options. Another big advantage of both of these is that due to their iron content, the electrode tracks can be visualized using Prussian blue staining. This makes these metals critical for those that are doing studies where they really need to be able to visualize the electrode tracks very accurately. However, some disadvantage of them is that they do offer poor stimulation performance unless the surface area is very large. They both have large charge transfer capacity, low charge transfer capacity and electrochemical stability, and they both corrode readily in many conditions. Through the presentation, we'll be speaking a lot about impedance. Impedance is a complicated topic because many times, the same impedance range in one type of electrode will give different performance in the body compared to a different electrode type. For instance, for the MEAs, where the electrode is the very tip of the electrode, versus the LMA, where the electrode is along the side of the electrode, the same impedance will tend to pick up different populations of neurons, which is why any discussion of impedance should be considered more of a rule of thumb. We always encourage researchers to experiment with different impedance ranges to determine which works best for their particular application and target. However, this can give you a good guideline of what to expect from different ranges. The highest impedance range is above 1 megohm, 1 to 10 megohm. This range is typically used for researchers that are trying to achieve well-isolated single-unit recording. Impedances in this range really only amplify neurons very nearest to the tip, but the trade-off of that is that they're very sensitive to environmental noise and artifact. For this reason, those that want electrodes at very high impedances in this range, we typically recommend only for fixed in vitro preparations and acute recording, where there's a great degree of control over the environmental noise and the shielding. For those that are doing in vivo recordings in behaving animals, typically recommend going to a slightly lower impedance range of 500 kiloohms to 1 megohm. Electrodes in this range typically offer a great balance between multi-unit and single-unit recording, isolation, and yield. For this reason, it's probably the most popular range of impedances for those that are doing chronically implanted arrays in behaving animals. The impedance range below this, of 100 kiloohm to 500 kiloohm, is the range for most of those researchers that are doing local field potential and microstimulation. It's the highest impedance range we typically recommend for microstimulation, simply because at this impedance range, it becomes easy to enter into unsafe voltage ranges upon reaching the currents required to elicit the physiological response you're looking for. Because of this, it really requires careful monitoring to ensure safe voltages. When I say safe voltages, there's a number of different things that go into that. But most commonly is that you want to keep the voltage within the water window. That means that beyond this voltage, you're likely to see hydrolysis generated on the tissue, on the electrode surface, and the tissue starts creating things like hydrogen bubbles, really damaging the tissue. So, of course, it's always a good idea to stay within that range. The next impedance range below 100 kiloohm is typically those that are doing mostly stimulation as well as wide area LFP. Impedances below this range are typically reserved types of impedance you'd expect to see from things like ECOG electrodes, very large electrodes for deep brain stimulation and things like that. Many researchers commonly ask, what's the relationship between impedance and surface area for the electrode that they're using? This, of course, varies depending on what metal you have selected for your electrode, as each metal has a different concomitant impedance, as I mentioned earlier. And this chart really illustrates that point, where you can see the pure iridium electrode at the very bottom, the black line, tends to offer much lower impedances at the same surface area as the other metals that you see, with the highest being the alloy and stainless steel, the red line at the top, which has much higher impedances for the same surface area. For this reason, it's important to understand exactly what metal you're using and how that relates to what neurons you're going to be targeting. Especially for those that are targeting very, very small cortical regions and small animals, it becomes an issue where to get the impedance that you require may require an electrode surface area that's larger than you would prefer, especially if you want to only record from a small population of neurons. This chart is also available in a higher resolution on our webpage, or you should absolutely feel free to email us if you have any questions on the proper way to design your electrodes for your particular target. Many researchers also ask us how to maximize the yield of their arrays. Yield is a fairly complicated topic, and many things go into it. There's a lot of different elements that go into whether your array and implantation will be successful or not. One of the most important elements of that is, of course, the planning, especially for those that have complicated or hard to reach targets. Determining the proper surgical path for your array is very important, especially for those that have, say, mid-sagittal targets such as PFC and rodent, or lateral targets such as barrel cortex. They may require either a special probe design or approaching them from a particular angle. This can be very important, and it's something you need to consider when designing your array. Surgical technique is also very important. We always encourage surgeons to get as much training and practice as they can, because a lot of the complications that you would see during a surgical procedure can go a long way in determining how the array is going to perform chronically. It's always a good idea to minimize implantation trauma, bleeding, routes of infection. It's also important to select the proper impedance, as I mentioned earlier. You want to select the optimal impedance for your desired signal and probe design. Something that's important to note is that post-implantation impedance does not correlate well with yield. Impedance of an implanted array will fluctuate quite a bit, as the inflammatory process progresses. Typically follows a fairly consistent progression within the first 2 weeks, but after that you will see impedance fluctuate a good bit. However, it has been shown that this does not really correlate with yield. However, impedance can be useful. We always encourage monitoring impedance throughout the implant just to monitor probe function, to make sure that all the channels are functioning and that there is no gross hardware failures such as cable failures or connector failures and things like that. It's important to note that yield will fluctuate up and down with all probes. It's important to note that to not assume that drops in yield are permanent. Something that we frequently observe is that a researcher will observe after 3 or 4 weeks of implantation an array suddenly going mostly silent, and they'll assume that the array has been failed for some reason. But then after a week or two, suddenly the array will come back to life and they'll achieve excellent yield. So that's why we always recommend continuing your study and continuing the recording, because it is very common for units to come back as the tissue relaxes. Common questions we receive regarding sterilization. For all of our products, we recommend low temperature ETO gas sterilization. ETO is typically performed at room temperature or near room temperature. It's a very gentle process. It does not harm any of the soft plastics that we use in our arrays. However, we realize that ETO is becoming more and more of a rare method because of the environmental and toxic issues with it. We've found that room temperature plasma, room temperature plasma hydrogen peroxide methods such as steroid or vaporized hydrogen peroxide are becoming more and more common. We do not have a good amount of testing done with these because they're new methods, but the feedback that we have gotten so far has been great. Researchers do recommend that if you use hydrogen peroxide methods, to make sure that the probes are very clean, because some researchers have observed things like bubbling on the surface after the hydrogen peroxide treatment. We believe that maybe from like any kind of residues or oils on the probes that were left from handling. So always make sure the probes are very clean and pristine before using these methods. Autoclave may be used on some products, essentially those products that have mostly metal and hard plastics. But if you have a different method available, it's always recommended to use the more gentle method, because heat and moisture can distort thin polymers and corrode electrode surfaces more quickly. It's also not appropriate at all for soft plastics or silicones or carbowax coatings. This makes autoclave completely inappropriate for things like FMAs and MWAs, which incorporate carbowax, as well as anything with a flexible cable. The issue is that the heat can cause the silicone in the cable to soften, which can release built-up stresses within the microwires within the cable to cause it to distort away from its initial orientation. We always recommend avoiding chemical immersion methods that can leave residue. Common question that we receive is whether or not alcohol immersion is appropriate as a primary sterilization method. It is not, and most institutions and IACUCs will forbid its use as a primary sterilization method. Alcohol tends to leave a lot of spores viable and a lot of other pathogens, and so we always recommend not using it, though alcohol can be used as a secondary method, such as between multiple implantations in the same session. Now I'd like to go into a brief product summary of a number of our most popular product categories, beginning with our monopolar single electrodes. These electrodes are actually the basis of a number of our other array products, which is why I'd like to describe these first, because a lot of the options that are available for these are also available in arrays. As an overview, these are insulated electrodes. They're available in multiple metal selections, tip profiles, lengths, diameters, and impedances, and I'll go into those later. All of these electrodes have a vapor deposited parylene C thin film, approximately 3 microns thick. They are also available with an optional polyimide jacketing for those that really need to have a more robust insulation and stiffness of their electrodes. Typically those that are using very thin electrodes but need them to be able to handle a good bit of use and bending resistance. We typically recommend adding an additional layer of polyimide. All of these electrodes are electrically chemical etch tapered to a 1 to 6 micron tip. And the tips are then arc exposed to whatever impedance the customer requires. For those customers that also, need, instead of impedance, are more looking for a very precise surface area, we do offer laser removal. In which case, the electrodes are observed under a microscope, and then, the insulation of the tip is removed piecewise, using a very powerful laser. There's some tip profiles available. We've got 4 standard tip profiles. The first is is our standard tip profile A. This has a 3 micron parylene C coating and is exposed tip with a 25:1 taper. We found that the standard tip profile is acceptable for most researchers. It gives a very good balance between sharpness, penetrating power, as well as tip resilience to bending and hooking. For most researchers, the standard tip will give very good performance. Some researchers, however, prefer more of a blunted tip. The blunted tip is essentially the same as the standard tip, only has an additional electrochemical process subjected to it in order to remove the sharp tip and reveal more of a blunted tip. As far as the performance difference between standard or blunted, a lot of times this is relative, with researchers preferring one or the other. Many researchers that claim that blunted works better state that it's because they feel that the blunting helps shift the tissue out of the way instead of cutting through it. Some claim that it offers more of a point source for stimulation as opposed to the standard, which is more of a cone source. This is why we always encourage researchers to try one or the other, just to see which works best for you. The heat-treated tapered tip profile is for those that intend to insert their electrodes through tough tissue, such as dura, other tough membranes. How this works is that, because often for those that are trying to insert a standard electrode through a tough membrane, it can end up pushing the soft insulation layer back, changing the impedance of the electrode. Often, this becomes more and more a problem with repeated insertions. The heat treatment actually hardens and bakes the insulation, causing it to become more resilient and stick more to the electrode surface. This allows it to hold up to multiple insertions without being pushed back from the electrode. The 4th tip type is our extra fine tip profile. These tips are subjected to a completely different vapor deposition process and etching process, which creates both a thinner parylene C layer of only 1 micron instead of 3, as well as a much sharper tip of a 40:1 taper. These tip profiles are great for those that need to have a good deal of extra sharpness and thinness on the tip of the electrode. Often for those that are doing studies in vitro that really need to have a very precise point and a very small implantation tract to avoid damage. However, the trade-off is that these tips are much more susceptible to things like bending and hooking. Because they're so thin and slender, really any deviation from a perfectly straight implantation will result in the electrode tip being bent, and thus these are not really recommended for those that are doing repeat implantations. Some common questions. Most of these electrodes can be acutely reused many times. Several researchers have reported over 20 to 30 insertions with the same probe. The caveat is that the probes must be cared for properly between implantations. It's important to avoid bending the shaft and blunting and hooking the tip. Always inspect the electrodes between implantations to be sure that the tip is not hooked. Especially do this under a microscope, because a lot of times it's very difficult to see with the naked eye. This is very important because if you try to implant a hooked tip into tissue, it will end up cutting through the tissue a good bit more, causing a lot more implantation trauma and possibly deviating the path of the electrode as it passes through the tissue. It's important to clean the electrode carefully between sessions. We recommend a 2-step process of sonication and electrochemical bubbling. Sonication itself is a multi-step process. It's intended to remove some of the bulk debris, such as tissue residue, blood, things like that that adhere to the surface. First step is to sonicate for roughly 5 minutes in a 50% household bleach solution. followed up by another 5 minutes in a deionized water solution to remove the bleach, and then for 2 or 3 minutes in an alcohol solution to assist in drying. Alcohol should only be used in electrodes with hard materials. Alcohol does soften silicone gel, so it should not be used on electrodes, or at least it should not be used for very long on electrodes with flexible cable or any type of soft silicone. Also, I'd like to note that the cleaning protocol is included within a pamphlet in the products that we sell as well. If you have any questions at all on the proper way to clean your array, definitely get in contact with us without hesitation. Electrochemical bubbling is a very important process that returns the actual electrode surfaces to a mirror finish. How it works is that you apply a constant voltage of -3 volts. It's very important to note the polarity of this. You want to make sure that the negative pole is connected to the electrode, as if the positive pole is connected to the electrode, it can actually drive the metal to corrode and ionize into the solution. Common way to generate this voltage is by using just 2 AA batteries in series. Is an excellent way to do it. You'll know that it's working because it'll start creating some pretty vigorous bubbling on the surface. Again, this is the hydrolysis that I mentioned earlier. This bubbling tends to knock off oxidation or any other crust that is developed on the electrode surfaces. We've noted that it's a common complaint among customers that, especially those that are storing their electrodes or arrays for long periods of time, that when they actually open their array and measure the impedance, it's much higher than the impedance that they specified. A lot of times this is because, even though the materials are mostly noble, they do corrode over time. Typically, we suggest that they do an electrochemical bubbling process, and they note that the impedance immediately will go back down to the specified values. Another benefit of electrochemical bubbling is it allows you to detect things like short circuiting as well as insulation damage. It's important to note that any exposed metal within the electrolyte that's subjected to this potential will create hydrolysis. Thus, if any bubbling is seen anywhere but the very tip of the electrode or at the recording site for LMAs, that means that the insulation may be damaged. If you see multiple channels bubbling, that means you've got a short circuit between channels. It's going to be a great way to diagnose issues between electrodes. It's also very important to monitor the impedance of electrodes between uses, just to make sure that the contact sizes are still the same size, that everything is functioning properly. It's never recommended to reuse chronically implanted electrodes or arrays, any type of electrode or array. Typically, if an electrode or array is implanted properly, it's going to be encased in a number of hard materials such as dental acrylic or silicone gel or other things like that in order to secure the array in place. Many researchers that have tried to reuse chronically implanted electrodes, typically they explant the array and then try to chip away at the dental acrylic or whatever that's encasing the array. It's very, very easy to damage the array or the insulation during this process, which is why we never recommend using it, particularly for studies that are collecting data for publication, because it's nearly impossible to assure that the array will perform the same between chronic implants. As I mentioned earlier, we do have polyimide jacketing available. This is great for researchers that are immersing electrodes deep in electrolyte or tissue, like implanting electrodes beyond 10 millimeters or into an electrolyte bath, such as for tissue slices or other procedures in vitro. What this does is that it decreases things like leakage currents and capacitive shunting. It also provides a good deal of additional stiffness. We also received a question: what is the acceptable tip length for single electrodes? So the tip length will, I'm assuming that when you say tip length, you're stating the length of the exposed tip. As I mentioned earlier, this will change depending on the impedance that you select. Of course, if you would like a lower impedance, that typically results in a much greater tip exposure. As far as the length of the actual electrode, we can make electrodes up to a broad variety of lengths. Sometimes over 100 millimeters if you request. It's always recommended to understand the shielding requirements for the signal that you're collecting. Especially for high impedance electrodes that are outside the body, you need to make sure they're properly shielded, or you will pick up a good deal of environmental noise.